Okay, so continuation of free radical reactions. Today we will discuss about hydroxylation of aromatic hydrocarbon. So hydroxylation using free radical. So that means Fenton's reaction, otherwise Fenton's reagent. So what is Fenton's reagent? So Fenton's reagent is the one which contains ferrous ions. Ferrous ions. Ferrous ions, when it is treated with hydrogen peroxide, so there will be a liberation of hydroxyl radical and also a hydroxyl anion. So in this process, iron is giving one electron, losing one electron, and itself it's converted into ferric. After taking a electron from the ferrous, hydrogen peroxide is splits into hydroxyl radical and hydroxyl anion. Let's give an entry. Okay. So hydroxyl hydrogen peroxide, when it is treated with ferrous ion, uh, hydrogen peroxide is split into hydroxyl radical and hydroxyl anion. The obtained hydroxyl radical, it reacts with benzene. No, you know that CH undergoes homolytic cleavage, and the obtained phenyl radical react with the hydroxyl radical, giving rise to phenol as the product. So overall, in this process, a benzene is converted into phenol. So for this, the Fenton's reagent is hydrogen peroxide in ferrous ion. So in this process, ferrous is giving electron. The electron used by hydrogen peroxide converted into hydroxyl radical and hydroxyl anion. The obtained hydroxyl radical made to react with benzene. So that means CH bond undergoes homolytic cleavage, forming phenyl radical. That phenyl radical react with hydroxyl radical, giving rise to phenol as the product. In the next step, let's look at the mechanism. So iron means ferrous ion, it gives electron converted into ferric. Once the electron is released from the ferrous, that was taken by hydrogen peroxide, and the split this hydrogen peroxide into hydroxyl radical and hydroxyl anion. This hydroxyl radical again make to benzene undergo homolytic cleavage of CH bond. So giving rise to phenyl radical. The phenyl radical again react with one more equivalent of hydroxyl radical, giving rise to phenol. So this is about the mechanism how the benzene is converted into phenol, and the role of iron means a role of ferrous in reaction with the hydrogen peroxide. So with this, I will go to the next concept. So that is reactivity of free radical at aliphatic substrate. Reactivity of free radical at aliphatic substrate. Aliphatic means aliphatic compound. So here I am taking ethane as the aliphatic compound. So ethane, when it is treated with chlorine, okay, so more particularly chlorine radical. So what will happen? This CH bond undergoes homolytic cleavage, forming a ethyl radical, and there will be a liberation of HCl neutral product. And here the energy is required -3 kilocalories. The minus indicates that it is a feasible reaction as per the thermodynamics. Suppose uh, the formation of radical and then reaction of this formed radical with chlorine. So that means ethyl chloride. The ethyl chloride is not formed in this reaction because it requires 18 kilocalories per mole. So that means it's a what is called endothermic reaction, and this much energy is required to form a ethyl chloride. So, whereas the formation of ethyl radical does not require much energy, it is a exothermic reaction. So that means ethyl radical means aliphatic radical easily formed compared to the alkyl halide. So that's what you need to take it out from this slide. So with this, I will go to the next slide. So here, a radical, more particularly secondary radical. So if there is a presence of secondary radical, the adjacent means alpha carbon containing CH cleavage, so giving rise to alkene as the neutral product, and of course there is a liberation of hydrogen radical. So this is with respect to the secondary radical. Suppose a compound, okay, more particularly you can observe that allylic hydrogen. This is a allylic hydrogen. So allylic hydrogens are acidic in nature, and this allylic hydrogen easily undergo homolytic cleavage, so giving rise to radical. Let's give an entry. Okay. So allylic radical undergoes homolytic cleavage, so giving rise to allylic radical. Allylic compound is converted into allylic radical. So again here the obtained allylic radical is stabilized through resonance. That means this pi bond undergoes homolytic cleavage, so there will be a double bond formation and there will be a radical formation. So that means these two are in equilibrium, these two are canonical form, these two are resonance form. So what it means? Allylic radical easily forms a free radical, and the obtained radical is stabilized through resonance. And what is the another thing? This CH bond is called vinylic hydrogen. The homolytic cleavage of vinylic hydrogen is not possible. Because of that, no product formation. So that means what it means? It means that allylic hydrogen can be cleaved using homolytic fashion, whereas vinylic hydrogen is not possible to cleave homolytic fashion. That's what you need to take it out from this slide. And one more concept that's called benzylic proton. So that I am explaining in the next slide. So this is a benzylic proton. More particularly, the proton attached to alpha carbon is called benzylic proton. It is also possible to make to homolytic fashion of cleavage of benzylic proton, and the benzylic radical is formed. The obtained benzylic radical is stabilized by resonance. That is no problem. But suppose here if there is a electron withdrawing groups are attached. So electron withdrawing groups or electron donating groups are attached to alpha position. In such cases, Free radical homolytic cleavage occurs at the beta position. That's what you need to remember. So that means if there is no substitute on the benzylic carbon, homolytic cleavage occurs at the benzylic carbon. Suppose if there is a substituent, the substituent may be an electron withdrawing group is attached to the alpha position. In such cases, free radical is formed at the beta position. That's what you need to take it from this slide. So with this, I will go to the next slide. So next is about the reactivity at the bridge head position. So now this position is called bridge head position. It's a name reaction. I think Hans-Decker reaction. So conversion of silver carboxylate into halo compounds. It's a name reaction. So the bridge head. So normally one can frame a question on this. So write a note on reactivity at free radical reactivity at bridge head position. So there is a 5 marks question on this concept. So it's again a name reaction, and again, so there is a possibility of forming a free radical on bridge head carbon. So you know that normally a anion at the bridge head carbon is difficult because of the steric hindrance. So that is the reason. But since it is a radical and bridge head radical formation is possible. Okay, and it's a name reaction. It is possible to convert a silver carboxylate into a halo carbon. And then I will go to the next slide. In the next slide, I am explaining about the difference between the allylic proton and the methyl proton, and also I am explaining about the formation. So formation of halo compounds. Halo compounds means replacement of allylic hydrogen or the replacement of methylic hydrogen with respect to the different kinds of halogens. So that I am explaining in the next slide. So look here, I am taking allylic proton. This proton is called allylic proton, and this proton is called methylylic proton. But what is, suppose a cyclohexane is subjected to chlorination, it is possible to form a two kind of product. Suppose a allylic proton is obstructed, then there is a allylic halogenated compound is the major product. But in addition to the allylic halogenated product, so there is also a methylylic halogenated product that is of around 38%. Suppose if you are using a bromine as the halogenating compound, in that case only the selectively the allylic proton is replaced with bromo compound, which of about 95%. That's the speciality about the bromine. So that may be because of the bulky group. Okay, bromine is bulky compared to the chlorine. So this is the difference you need to remember. So usually one can frame the questions on this kind of thing. Why? Because in the case of bromine, selectivity is there. In the case of chlorine, there is no selectivity. There is a mixture of products is obtained. Okay, so this is under the reactivity of attacking radicals. So here, in this case, chlorine is attacking radical, and in this one, bromine is the attacking radical. So what I will do with this, I will go to the next slide. So here I get continuation of attacking radical. So what I am taking here, a isobutene. A isobutene, when it is irradiated, okay, when it is irradiated in presence of light, in present with chlorine as the uh, reactant. So there is a possibility of forming a two product. One is what is called as a tertiary halide and a primary halide. So both are formed in equal quantity, almost equal quantity. So let's give an entry. Right. Okay, so that means isobutene, when it is subjected to chlorination, a chlorination, when it is irradiated in presence of light, it gives almost equal quantity of a mixture of products. Suppose a same isobutene, when it is irradiated in presence of light with the bromine, it exclusively, okay, gives single product, that is a tertiary halide as the product. So that's about the what you call attacking species, attacking nucleophiles. So with this, what I will do, I will go for a electrophilic substitution reactions. That means aromatic one. So let's go to the aromatic one, moiety. Reactivity of free radical at aromatic substrate. So as usual in the case of electrophilic substitution reactions. So electrophilic substitution means suppose if there is a substituent is already present in a benzene ring, that substituent orient the incoming group, okay, to the moiety. Suppose electron donating group is present, it will direct the incoming group at ortho position as well as para position. If electron withdrawing group is present, it will direct the incoming group to the meta position. So free radical substitutions at an aromatic carbon, it also takes place the mechanism in which a ring hydrogen, here hydrogen CH of the aromatic moiety is abstracted and it gives an aryl radical, and that aryl radical is stabilized through resonance, and finally there will be so electrophile is attached and the product is formed. So this is a general reaction I'm taken. So Z may be a electron withdrawing group or may be a electron donating group. So Y may be a radical. So let's look into the characteristic features of the electrophilic substitution free radical reactions. So the following generalization have been made regarding the reactivity in aromatic substrate. All substituent increase the reactivity at the ortho and para position as compared to the benzene. Okay, suppose if there is a substituents are present in a benzene ring, then reactivity takes place at the ortho and para position as compared to that of the benzene. And here there is no great difference. There is no great difference between the electron donating and withdrawing groups. So this is because radicals are neutral species and are not influenced by polar properties of the substrate to any significant extent. Okay, and reactivity at ortho position. So reactivity at ortho position is greater than that of the para position, except where there is a large group decrease orthoreactivity due to steric hindrance. Although hydrogen is the living group in most free radical aromatic substitution reaction. So ipso attack. So ipso attack means suppose a substituent is present in a benzene ring. If the uh, uh, free radical is attacking the position where there is a substituent is present in a benzene ring, such reactions are called ipso attack. In this one, nitronium radical attacks the methyl group substituent which is present on a benzene ring and giving rise to nitrobenzene as the product. That means it's called ipso attack. Ipso attack means a nucleophile. So in this case, free radical is the nucleophile. Nucleophile attacks the benzene ring where there is a substituent is present and replaces that substituent, and is called ipso substituted products. So this is about what is called as ipso attack of free radical to the aromatic moiety. So this is about what is called as free radical reactions. So in the next slide, I'm I'm mentioning the few questions. So what you can do, you can take these questions as a assignment and write the answers. Okay, and you can you have to show when you are coming for the offline classes. Maybe you can note down the questions. So the first one, predict the product and propose a mechanism. Here NBS is used and AIBN is the radical initiator. So, and what is the substrate? Toluene is the substrate. And you need to identify bromine where it will attack and what is the product formed. So write briefly on the mechanistic aspects of Sandmeyer's reaction. It's a direct question. You can write the reaction as well as the mechanism and also one or two examples. And predict the product and propose a mechanism. So this is again what is called as a primary amine. It is, when it is treated with sodium nitrate in presence of dilute HCl, it will give you diazonium chloride. The diazonium chloride, when it is attacked to alpha beta unsaturated compound, so what is the product is formed. So that you have to identify, that you have to write the mechanism as well as the product. And here I am taking this is name of this compound is called parathymine. So parathymine, when it is treated with uh, when it is irradiated in presence of air, this is also a oxidation. So you can write what is the product formed, and also you have to write the mechanism. And this is again what is called as a name reaction. Silver benzoate, when it is treated with bromine, what is the product you will get? You have to write the product and write the mechanism. So note down these questions and write it in a separate notebook and you submit when you are coming for a offline class. So with this, I will go to the next slide. Next slide also, I am displaying few more questions. How do you achieve the following conversion? So conversion of silver benzoate to bromobenzene. Highlight the mechanism involved. So here you have to write the what is the reagent used here, and you have to write the mechanism also. So it's a name reaction, Hunts-Decker reaction. Predict the product and propose a mechanism for the following. So aromatic compound, when it is irradiated in presence of light with chlorine. What is the product? Isoptile. You have to write the product and also write the mechanism. So how do you explain the stability of tertiary radical over primary radical? It's about the stability one. So tertiary radical and primary radical. So stability of the radical you have to discuss and you have to give the order. So tertiary radical is greater than secondary, secondary is greater than primary. That explanation you have to give. So what are the bridgehead radical? Give example and explain the role of neighboring group assistance in free radical reaction at bridgehead carbons. So here two questions is combined. So one is a bridgehead radical. You have to give example, and at the same time is also asking about the neighboring group participation in the bridgehead carbon formation. And one more question, how do you achieve the following conversion? Propose suitable mechanism. Here, a aniline is converted into chlorobenzene. So that means it's again, this is also a Sandmeyer reaction. Give the evidence to support the formation of the ensuring reactive intermediate. Okay, this is one additional thing. Maybe you can look into the organic synthesis by Smith or reaction mechanism by Peter Cycus, and you have to answer for this. It's better you can look into the organic synthesis by Smith, okay? Because your syllabus is framed or organic synthesis. Some of the questions or answers you can get it from the Smith. More particularly, you have to get the information about evidence supporting the formation of ensuring reactive intermediate. So this part you can get it. This is okay, name reaction, it's a Sandmeyer's reaction. But the evidence, you can get it from the Peter Cycus or Smith. Write briefly Mervyn annihilation. So it's a direct question, it's a name reaction and you can answer. So tell me, is there any doubt up to this, more particularly in the free radical mechanism? Hello?
No, sir.
No. Okay. Maybe. Okay. Now what you can do? You answer for the a few mentioned in this slide as well as the previous slide. And if we are getting a few more questions from the different question papers, more particularly BCU1, take it out and answer it in a separate notebook. So this, with this, the free radical is completed. Maybe next class onwards, I will discuss about biochemical mechanisms. Okay, I will